Welcome everyone. Today we'll be talking about layout planning models and design algorithms. These are the topics that we will be talking about in this video. Last week we built the foundation, layout types, SLP, and the pairwise exchange algorithm. This week we go deeper into algorithmic side. We cover how all algorithms are classified, which input data they accept, and then work through three major approaches in detail. The graph-based method step by step, block plan's unique conversion process, and the MIP formulation that treats layout as a formal optimization problem. So let's talk about algorithm classification. All layout algorithms fall into two main categories. Construction algorithms build a layout from scratch, no initial layout is needed. The graph-based method, LDEP, and CoreLab are all construction algorithms. Improvement algorithms start from an existing layout and seek better arrangements through systematic exchanges. Pairwise exchange, craft, mcraft, and multiple are improvement algorithms. Three algorithms sit in both categories. BLOCPLAN, Logic, and MIP. Of these, BLOCPLAN is the most practically important. It can either build from scratch or improve an existing layout, and it accepts both qualitative and quantitative input. MIP, despite being categorized as construction, is really a formal optimization framework rather than a heuristic procedure. So, the type of input data an algorithm accepts determines which objective function it can use. As you can see here, qualitative input has a different objective. It's adjacency based. Quantitative only is distance based objective. And if they're both, it's a block plan converts from two chart to a relationship chart through a flow between chart. The practical rule, if you have flow data, use it. If you only have organizational relationships, the qualitative tools are your only option. If you have both block plan, is likely your best starting point. Now let's talk about graph-based methods, concept and considerations. The graph-based method is a construction algorithm using the adjacency-based objective. It places departments one at a time, selecting each based on which placement maximizes total adjacency score with already placed departments. Four important limitations to understand before applying these method. Adjacency score ignores distance. Two layouts with identical adjacency scores can have very different total material handling cost. The graph-based result should always be verified with a distance-based evaluation. Now, department dimensions are ignored. All departments are treated as equal size. The length of the shared boundary between adjacent departments is not considered. A small shared wall counts the same as the large one. Planetary required, but rarely achievable. Graph arcs should not intersect, but the relationship diagram from a real facility is almost always non-planar. The method forces planarity, which may distort the result. And finally, sensitivity to numerical weights. Small changes in the weights assignments can change which departments are selected and the final layout of its dependency. As you can see here, we have five departments. The relationship chart gives us pairwise adjacency weights. All weights are visible as you can see here. For our first step, we select the department with the highest weight. The maximum is 20, as you see here. Departments 3 and 4. These two enter to the graph first, connected by a line with the weight 20. Now, for the second step, select the third department. For each remaining department, sum its weight to the already placed departments 3 and 4. Now, we selected department 2. So department 2 scores 25, the highest. It is added to the graph, connected to both 3 and 4. The graph now forms a triangle, 3, 4, 2, with the weights 20, 13, and 12. Now, when we get to step 3, select the fourth department. Now we have departments 2, 3, and 4. For each remaining department, sum all the weights, as you can see here, to the three placed departments. When we do this, we select Department 1. Department 1 scores 27. The new node for Department 1 must be placed on a face of an existing triangle. Make sure you don't forget this. A face is any triangle region bounded by three connected nodes. The triangle 2, 3, 4 has one internal face, and three external faces. Department 1 is placed on the face that maximizes adjacency. In this case, the face bounded by 2, 3, and 4 works. The graph now has four nodes with the connections. Now, for step 4, we place the last department, department 5. Its weights to be placed departments are, as you can see here. We evaluate which face of the existing graph gives the highest adjacency score, department 5. Here we can see that 1, 2, 4 and 2, 3, 4 faces are the best. When a tie occurs, either is a valid choice. Both produce different but equally scored layouts. By convention, we select 1, 2, 4 as the first tie encountered. Now, let's talk about block layouts. We convert the graph to a block layout. Each node in the graph becomes a rectangular department block. Adjacent nodes in the graph become physically adjacent departments in the block layout. The arc weights are captured, meaning the pairs that end up adjacent in the block layout give us a total adjacency score. Summing all captured adjacencies, we get a total of 81. Now remember, the maximum possible score would require all pairs to be adjacent, which is geometrically impossible. The adjacency score of 81 tells us how much of the total relationship weight this layout captures through physical adjacency. Now let's move to the block plan. Block plan stands out for three reasons. First, it accepts both relationship chart and a from to chart as input. No other algorithm covered this week does that. Second of all, it can be used as both construction algorithm and improvement algorithm. And finally, it evaluates layouts using both the adjacency-based objective and the distance-based objective, giving you two independent measures of layout quality. Departments in BLOCKPLAN are arranged in horizontal bands across the building footprint. The algorithm generates multiple layout alternatives and evaluates each. The best layout by the selected objective is then recommended. Now, BLOCKPLAN's unique conversion procedure turns into a quantitative from to chart into a qualitative relationship through 5 steps. One second. Now, for step 1, we build the from to chart. Step 2, build the flow between chart. Step 3, we have to find the maximum Gij and divide by 5 to get the interval width. After that, we assign ratings based on which band each Gij falls into. And finally, we convert numerical weights to create the numerical relationship chart. BlockPlan evaluates layouts using two scores. The adjacency score, where Xij equals 1 if the departments I and j are adjacent. This sums the flow weight for every adjacent pair. The normalized adjacency score, also called the efficiency rating, uh, is equal to, as you can see here. The denominator is the sum of all flow weights, regardless of the adjacency. So the normalized score tells you what fraction of total flow is captured by adjacent pairs. A score of 1 is perfect. All flow occurs between adjacent departments. A score of 0.63 means that 63% of total flow is adjacency captured. In the 8 department worked example, both the initial layout and block plan's final layout produce the same adjacency score of 15 and the same normalized score of 0.63. If you evaluated solely on the adjacency-based objective, you would conclude that layouts are equivalent and block plan offered no improvement by evaluating on the distance-based total cost. The adjacency-based score missed the improvement entirely. This is exactly why the slides say when the adjacency score is equal between two layouts, evaluating using the distance-based cost before making a final decision. Now, let's talk about our concept and parameters for mixed integer programming. The mixed integer programming formulation treats the facility layout problem as formal optimization model. The key assumption, all departments are rectangular. Under this assumption, specifying a department's centroid coordinates and its length or width completely defines its location and shape. No other layout algorithm models departments this precisely. MIP is a construction type model. No initial layout is needed. The solver determines the optimal arrangement directly. The objective uses rectilinear distance between centroids weighted by flow and cost. Parameters the model needs. Building length Bx and by By. Area of each department AI and upper and lower bounds on the length and width of each department. These bounds prevent departments from becoming degenerate shapes. A department can't be 1 foot wide and 1,000 feet long just to satisfy its area constraint. So, the continuous decision variables define the geometry. Alpha and beta are the x and y coordinates of each department's centroid. Xi and Xi2 are the left and right boundaries. Yi1 and Yi2 are the top and bottom boundaries. The binary variables are what make this what make this an integer program. If Zixj is equal to 1, department I is strictly to the east of department J, meaning department I's left boundary is at or to the right of department J's boundary. These binary variables capture the relative spatial positions of departments' pairs. They're used to enforce both the positional constraints and the non-overlap constraints. As you can see here, the objective function, 6.5, minimizes the sum of these to find the rectilinear distance between the centroids weighted by flow and cost. Constraint 615 is the most important. It guarantees no two departments occupy the same space. Without it, the optimizer would stack departments on top of each other to minimize distances. And this will be all for our week. Thank you for listening. You now have the full kit for layout planning from SLP procedures all the way to formal MIP optimization. Thank you for listening and have a good day.